This is a classic circular motion type problem. We've got a car going around a flat curve and a coefficient of friction, and we want to decide whether this car can stay on the road or not. Keep in mind we've got force. Sum of the forces is equal to ma. We've got acceleration circular is v squared over r, and then we've got v is equal to 2 pi r over t. At this point, 2 pi r over t is probably not going to be very useful because I don't have any information about time. Let's go ahead and draw a force diagram. Whenever you're starting with car going around a curve, you want to draw two diagrams. You've got the car going around in a circle, so you draw your curve. We know the radius is 25 meters, so we've got this radius 25 meters. And here's our car out here, heading around the circle in this direction. And we know the coefficient of friction is 0.8. Keep in mind, coefficient of friction, which we will probably need, is force of friction over force of normal. This is kind of why we need the second diagram, which is a side view. Here's the car. And we've got force of weight working on that downward. We've got force of normal in that direction. And then we've got the force of friction working towards the center of the circle. That is the net force. That's the only force that doesn't cancel out. And again, that will be our centripetal force because that's what's going to cause this car to go in a circle. So let's go ahead and figure out these forces. Fg should be easy enough. That's going to be mass times gravity, which is going to be 500 kilograms times 9.8 meters per second squared. So we get a weight of, there we go, 500 times 9.8, 4,900, 100 newtons. There is nothing happening in this direction, up and down. This car is not moving vertically, accelerating vertically. Motion is not changing vertically, so that means that the normal force is also going to be 4,900 newtons. So I can go ahead and figure out the force of friction at this point also. Coefficient of friction is equal to force of friction over force of normal. So that means that my force of friction is going to be equal to the coefficient times force of normal. So that's going to be 0.8 times that 4,900, which is going to wind up being 3,920 newtons in towards the center of the circle, because that's the frictional force that's causing this thing to go in a circle. So what we want to decide is whether he can make this turn, whether he's going to stay on the road. And this is the force of friction that's keeping him on the road. So what we're going to do is we're going to go over here, and I'm going to use the information here to figure out a force that's generated by this car going around this curve. So the first thing I need to do is figure out the acceleration so I can figure out that force. So the acceleration in this case is v squared over r. The velocity is 30 meters per second, so it's going to be 30 meters per second squared over the radius, which is 25 meters. So that means that the acceleration is going to be 30 squared divided by 25. So it's going to be 36 meters per second squared. That's the acceleration. So that means that the force is going to be equal to the mass of the car, which is 500 kilograms, times the acceleration of the car, which is 36 meters per second squared. So that's going to be, whoops, wrong one, times 500, 18,000. Wow, 18,000 newtons. Yeah, this guy's going off the road in a big way. He cannot make this turn. There's no way this guy makes the turn. Another way we can do this, this 18,000 is much greater than that 3920 that is supplied by the tires, so this guy's off the road. The other way we can do this is we can take this this force and figure out an acceleration. So this 3920, let me do it this way in a different color. This 3920 newtons is equal to that 500 times the acceleration. So that means the acceleration, the maximum acceleration that this car can generate before going off the road is going to be 3920 divided by 500. So 3920 divided by 500 is going to be about 7.8 meters per second squared, which again is less than 36. So 36 is what the car is generating by going 30 meters per second around the curve. He's not going to be able to keep the road. He's going off the road based on the acceleration. Another comparison I can make is I can use this acceleration, this 7.8 meters per second squared, and calculate the velocity max that he can take this curve at. So let's go ahead and do that too, just for kicks. So that 7.8 meters per second squared is equal to v squared over r. So that means that v is going to be equal to the square root of 7.8, 7.8 times 25, which is, that's times 25, and then square root the answer, and we get 14. So the maximum that he can take this turn at is 14 meters per second. He's trying to do it at 30. Yeah, this guy's dead. He's off the road. He cannot hold the road. So there's three different comparisons we can make. We can say that 30 is greater than 14. So can he make the turn? No. We can say that 36 meters per second, this is based on the velocity. This is based on the acceleration. 36 is greater than 7.8. So again, no, he can't make the turn. And then based on force, 18,000 is greater than 3920. So again, no, he cannot make the turn. Three different ways. I proved it 3 different ways.